All right, so my name is Koa Jacobson. Um, I'm just going to be pointing this at my computer, if that's all right, and I'm just going to be going over my final project. I'm presenting on the phase portraits of the fractional nonlinear Schrodinger equation. And one thing that I want to do with this presentation is kind of go over a lot of stuff that I wasn't able to include in my final paper. Here is a really good introduction to this kind of stuff. This is something that I looked at but wasn't able to incorporate just because of time. The Encyclopedia of Nonlinear Science, and then here I have a screenshot with some of their text quoted. The nonlinear Schrodinger equation can be derived as equations governing the evolution of weakly nonlinear wave packets in various media. So when I think of this, I think of like a traveling wave or a soliton is really what this paper that I was focusing on is about. They focused on the nonlinear Schrodinger equation, and they, in section 5, gave a qualitative analysis on this equation. Now this paper was really complicated. I admit that I don't understand a lot of it, and it's it was very complicated, but roughly this is the amplitude, this is the change in the amplitude from what I gather, and standard bifurcation theory can be applied to this equation. This is simplified a lot from the governing equation that is first presented. The Jacobian matrix and this kind of analysis is what I presented, and I just kind of copied these phase portraits and just tried to this is a first draft where I mistakenly forgot to change these, but yeah, I really just analyzed these, plotted out the phase portraits, or just tried to interpret them physically, really, and it was a really hard thing to do, actually. So just to kind of go over the basics, now that it's been a few minutes already, the nonlinear Schrodinger equation is, it describes propagation in a medium where there is nonlinear effects. So like interacting with the environment, interacting with the system, interacting with itself can happen, and it's really difficult. Some intuition that I tried to gather is like this kind of corresponds to the intensity if people have studied electromagnetism, and this kind of is a nonlinear focusing terms. I think it's like the Kerr effect here. It says that here. The cubic term accounts for the Kerr effect, which from my understanding kind of focuses waves, and the dissipative effects kind of try to spread the wave packet apart. So if you imagine that this is like a medium, a traveling wave would be like something like this, is the wave envelope moving. And what's really cool about the nonlinear Schrodinger equation is these equations are used in fiber optics to make it so that like the nonlinear effects and the dissipative effects cancel out, such that these things kind of stay stable, and you can do this over a long time. So in fiber optics, you're using like glass thin as hair. You can do it over thousands of kilometers. Yeah, thank you.